Thank you, Christoph. So we've heard a lot of talks now about deep scientific results. Mine is going to be a lot simpler because it is about the money. When I started working on perovskite silicon tandem solar cells, there was a story that I relatively often heard. It went something like this. I'm taking a silicon PV module, I'm putting some magic sauce on top of that magically increases the efficiency of this module to 30%. Doesn't increase the cost, I end up with a better module, so hence I should be better than the silicon PV module, right? Of course, I'm overdoing this a little bit, but I did hear versions of the story, and maybe you have too. I never found this quite convincing, and here's the reason why. I think that the entire setup of this was not entirely well defined, and I think there's a better way to look at this. And the way that I would ask you to think about the issue about tandem economics is the following. So we have two technologies, a solar cell A and a solar cell type B. Both of them cost a certain amount of money to produce, and both of them generate a certain amount of electricity. The tandem now is the third option, where I take those two solar cells, I put them on top of each other, I generate something that costs a little bit more to fabricate, and that generates a little bit more electricity. And the question now becomes, when is option C better than either of those two, better than A and B? We came up with a techno-economic model to describe this, and I'm not going to go too much into the detail, but I'm going to show you a plot about these details. This is a kind of phase diagram that you could think of this as a phase diagram, and this phase diagram has three largest area or three contributing areas. This window here is the one in which the tandems are optimal, and then we have two areas, one in which the top cell operated as a single junction is the best option, and one in which the bottom cell operated as a single junction is the best. As is often the case, if you generate a graph that looks very simple and nice, you end up with axes that are not quite as simple and nice. So what is plotted here, on the X and Y axis, is the ratio between the cost to make the top or the bottom cell and the cost to make everything else in the system. And the question, of course, is now, how do we end up here in this lower triangle where the tandem is the preferable option? Or even more so, how do we end up on this diagonal here within this window? And we found out that there are a number of factors that influence the shape or the size of this triangle, and one of these factors influences the size of this triangle, and there are a number of factors that kick you off the diagonal. And because most of the factors that kick you off the diagonal have to do with imbalances between the two technologies that you combine together, we came to call this the marriage of equals. Basically, whenever you have something that is different between the two technologies that you combine, you end up moving away from this diagonal and moving into a region where the tandem has a smaller advantage over either the two subsets that it's made of. So the single most important factor still is that the tandem needs to have a higher efficiency than either of the two cells that it comprises. So basically, this is to say that everything that has been done on tandem research trying to push the efficiencies is an absolutely necessary condition. You have to have the high efficiencies. You have to beat the single junction efficiencies for the tandem to make sense. But then anything that you can take from these two comprising technologies, and anything where you end up being unequal is becoming a problem. And that is really an issue for the perovskite and silicon tandem solar cells, for example. So examples for what throws you off the diagonal is if the two cells are at a very different technological level. Say if you can produce one of them at 85–90% of the Shockley-Queisser limit, and the other one is at 70% of the Shockley-Queisser limit. Another problem is if the fabrication cost of these cells are vastly different. If one is really very expensive and the other is very cheap, you're never going to be on this diagonal. You'll almost always find into the region where one of them is better than the tandem. You also want to have similar degradation rates. You want to have similar costs for integrating the cells into a system, right? If one technology requires more effort in that than the other one, you're again falling off this diagonal, and you're again not in the range where the tandem makes sense or makes the most sense. So this is roughly the framework in which we like to think about the tandems. We've done, of course, a lot of calculation also into the details. I want to just show you one example because it shows one feature that we've been seeing popping up time and again, no matter what kind of kernel configuration we've been calculating. The particular example that I'm showing here is a rather exotic tandem. It's one that consists of a cadmium telluride and a CIGS solar cell. One of the reasons that we looked into this was that we had a collaboration with First Solar at the time that was done when I was at MIT. And they were interested also in seeing what kind of possibilities do they have to generate a cadmium telluride based tandem. And we found that if we look into one of the big differences between the two, to answer the question whether tandems make sense depends on what kind of market you're looking into. And we've been looking into residential markets and we've been looking into utility markets. And in residential markets, we found that basically it's always the option that generates the highest yield, has the highest efficiency, that turns out best. So the 4 different colors, the symbols that you see here mark the 4-terminal tandem configuration, the 2-terminal tandem configuration, the cadmium telluride single junction, and the CIGS single junction solar cell. And no matter what we've been looking at, either the 2-terminal or the 4-terminal came out best in residential. But if we look into utility, it's almost always the lowest fabrication cost that trumps. So the cell that costs you least to fabricate, which was in this case the cadmium telluride single junction solar cell, is the one that ends up having the lowest LCOE. One more aspect that I wanted to talk about very quickly concerns the stability of the 2 subcells. I've already said that we want to have 2 cells that have equal stability. And I've been trying to find a good way to depict what happens if you have a cell that's less stable than another cell. And the way that I've been showing this here is these lines here that you find in this graph, these are ISO LCOE lines. So on all of these lines here, you have the same value of LCOE. In this case, it was something like 5 cents per kilowatt hour. The different lines here correspond to different project lives, whether you assume 20, 25, or 30% years of project life. And the x-axis marks the degradation rate and the y-axis marks the efficiency. So on all of these lines, you basically get the trade-off between efficiency and degradation rates. If I go from degradation rate 1 to degradation rate 2, how much do I have to improve the efficiency in order to compensate for this effect? And what we see is that the LCOE, but also other cost metrics, are extremely sensitive on the choice of degradation rate. So if I go from 1 to 2% annual degradation, the equivalent efficiency that I would need in one case is 20% and a 2% degradation. I'm already at the shock liquefier limit that I can get with a single junction solar cell. So basically what that tells us is that if you want to compete on the market with a solar cell, then you do not only have to have the efficiency, you have to have the efficiency, it's important that it's there. But if you cannot match the stability of whatever is on the market, you are going to have it very difficult, or it's going to be even impossible to establish that solar technology there. Okay, so to answer the question that I've been putting up in the beginning, when do tandem solar cells actually make sense? First thing is the efficiencies need to be right. We need to have a boost over both of the comprising single junction solar cells and not just the one. We need to be in the right market. High system costs are an advantage. Anything where we need to integrate solar cells, space, cars, buildings, have good opportunities for them, and we see a very clear path for how tandem solar cells can contribute into this market. In utility, it's going to be very hard, if not impossible, to get tandems to be the best option. And the third point is stability needs to be right. If you throw 2 technologies together, they have to have roughly the same degradation rates. Otherwise, it's not going to make sense. And with that, I am already at the end.